Okay, so today we want to talk about the derivative of inverse function. Okay, so first we have to know what is an inverse function. So whenever we say a function, it has to have, as I said, a domain and a codomain. So this is a function, which means for every a, we can find a unique b such that f of a is equal to b, and then because this b is a codomain, then it means every value of f must be within this set b. But there are basically two problems with the general function. The first one is, so for example, let's look at 1, 2, 3, 4, and 1, 2, 3, 4, 5. Okay, so then let me ask, is this a function? This is not a function, because 1 cannot be mapped into 2 points. So if it's a function, then it has to be something like this. Okay, and then my question is, so if let's say 1 is mapped to 2, then is this function 1-to-1? The answer is no, because 1 and 3 are mapped to the same point. So if this happens, then we say this function is not 1-to-1. But look at this function. If we just change this 1 into change the value of 1 into 1, then this becomes 1-to-1. Because if we have different inputs, then we'll have different outputs, right? So then this is called 1-to-1 function. Okay, so this is the first important definition. We say that f is 1-to-1. If and only if for all x and y in A, if they are different, then the values are different. And then by contrapositive, it is very clear that this is equivalent to say that for all x and y in A, if the values are the same, then it must be the same point, right? This is just by contrapositive, because P implies Q is equivalent to not Q implies not P. So this is what it means for 1-to-1 function. Okay, so another problem with the general function is that it doesn't need to be mapped to everything in the codomain. So now again, let's say 1, 2, 3, 4, and 1, 2, 3, 4, 5. Then you can see it can never map to all the points. So for example here, then you can see that 4 and 5 are not mapped by any point from x, from A. So maybe, in my notation, I prefer call it x and y, but it doesn't matter. So we say that a function is surjective. So if we delete these 2 points, then this becomes surjective, because every point in the codomain is mapped by at least 1 point, right? Because for example here, 3 is mapped by 3 and 4, or 3 and 4 are mapped to 3. That's what I mean. So 3 can be mapped, the value of 3 can be attained by 2 values. But each point here, from 1 to 3, can find some value in A such that it is mapped to this value. Okay? So if that's the case, then we say the function is onto, or it's surjective. So for 1-to-1, it's also called injective. And then here it's f is onto, or it's called onto, and it's also called surjective. So this means for all here it's a function from A to B, where B is a codomain, A is a domain. Then for all y in B, we can find at least some point x in A such that y can be mapped by x, okay, or x is mapped to y. So this is a surjective map, okay. Then we might be interested of the what it means to be surjective. Equivalently speaking, this means the range of f, which is the set of all f of x where x belongs to A, is exactly equal to the codomain B, right? This means, so in general, if we have a set, so let's say A and B, then for example this entire A is mapped, so it has to be mapped into a subset of B, right? This is called the range of f. And also it's denoted by f of a, like the image of a. So like every point here is mapped to some point here. Then you can see clearly that a function is surjective if and only if this range is the entire set B, right? I mean, in general, this is true, but this is not necessarily true for a general function. But if this is true, then it means every value in B is actually a value, right? I mean, every point in B is actually a value of f, which means you can find some x such that x is mapped to y. Okay, so this means that, so if you look at the graph, then it's clear that f is surjective if and only if the range, or simply f of a, is equal to b. So now, let's look at some function f that is both injective and surjective. Then we actually said that it is bijective. If and only if it's injective and surjective. But what does it mean? It means, for example, then the codomain must be the range, which means every point must be mapped by at least one point. And also by the one-to-one, or by the injectivity. It cannot happen that 2 points are mapped to the same point in y, in B, right? So what it means is that for each value y, you can find a unique x that is mapped to y. And also for each x, it is also mapped to a unique value y. So which means this becomes a one-to-one correspondence. So for each x, you can find a unique y. And for each y, you can find a unique x. So which means this becomes a bijective. So it's very symmetric, okay? And if it is bijective, then it is invertible. Then f is invertible. And then, which means for each y, we can find a unique value x. And then this map is denoted by f inverse. Okay, so this map is f inverse, while this map is f. So it's only when it's both injective and surjective that we can find an inverse function. So if it is invertible or bijective, I mean they are equivalent. Invertible means that we can find some f inverse, but by this graph, I think it's very, very easy to see that they are equivalent, if and only if it's bijective. So if this is bijective, then by the inverse, I mean, if f is a map from A to B that is bijective or invertible, then f inverse must be a map from B to A, such that two things are true. First, f of f inverse of every B or every y, it doesn't matter, is equal to B. Because if you go from a B to A and then you go back, then you get the same point, right? And on the other hand, if you go from A to B and then go back, then you still get A. So this is the criterion of inverse function. Okay? So this is a criterion of the inverse function. And now let me say something geometrically. So if you look at the graph, now let's assume that f is a function that is invertible. What about f of x? What about the graph of y equals f of x? And then the graph of y equals f inverse of x? What's the relationship between them? I mean geometrically. Geometrically, it means that, I mean, you should have learned it in high school, but if not, I will show you one example. So let's assume that f of x is e to the x. Then we know that the inverse function is ln of x, right? If you look at the graph, then this is e to the x. And then this is ln of x. You can see very clearly that they are symmetric along this line, which is the line of y equals x. And this is not a coincidence. This happens for each pair of a function and its inverse. The reason why it's true is because, for example, if this point is called, let's say, x naught comma y naught, what does it mean? It means, I mean, let's call this f of x, okay? And this is f inverse of x. So then this means that y naught is equal to f of x naught, right? And then because it's invertible, you can take inverse of both sides to get x naught is equal to f inverse of y naught, right? Because if you take f inverse to both sides, then f inverse of y naught is going to be f inverse of f of x naught. So then this will become x naught. So then this is true, which means x naught is equal to f inverse of y naught. But what is this point? This point is nothing else, but you just switch x and y. So then this becomes y naught and x naught. And the reason why this is also on the graph of f inverse is because this is exactly y naught comma f inverse of y naught. So then you can see this is x naught comma f of x naught. So this is on the graph of f of x. While this is f y naught, f inverse of y naught. So then this is on the graph of f inverse. And then you can see it just switch, right? You just change x into y, change y into x. And then geometrically speaking, this means you just reflect along this line, y equals x. So if you have some point here, then it just might be mapped to here. I mean, the graph is not accurate enough, but you can imagine that it should be true, right? You have a point and map it to here. If you have a point here, you just map it to here. Then, and also because it's symmetric, right? Because the inverse of inverse is itself. So if you mapped from here to there, then again, it's also symmetric. So which means the graph of the function and its inverse function has to be symmetric along this line. So now we might be interested what if the function f is differentiable? So now, for example, let's look at this at here. So here, if we have a tangent line at x naught, and then let's also look at the tangent line at y naught of f inverse, then you can see that their slope seem to have some relationship because their tangent line are also symmetric along this y equals x. So for example, if this line has slope 1/2, then this line must have slope 2, right? Because they are symmetric along this line. It's very clear because here 1/2 means that this is 1, this is 2, then this means this is 1, this is 2, right? It makes sense. Right? It makes sense. It's not just like a guess. You can prove it rigorously. Which means if you have two lines that are symmetric along y equals x, then their slope are the reciprocal of each other. Which means here, what is this slope? So let's call this slope k1 and this slope k2. Then this means k1, k2 is 1. Or let's say k2 is 1 over k1. Okay? But what is k2? K2 is f inverse of K2 is the derivative of f inverse at y naught. Okay? But then what is k1? K1 is the derivative of f at x naught. Okay? At x naught. Now, what if we want to find just this value? We don't want this x naught. We want to find what is x naught. So what is x naught? This is nothing else but what is x naught? X naught is, as I said, f inverse of y naught. So then this is f prime of f inverse of y naught. And this is true for any y naught, right? I mean, in the domain of f inverse or in the codomain of f. Then this means that in the correct domain, we have f inverse prime of x, which is the derivative of the inverse function at x. It is equal to 1 over f prime of f inverse of x. And the reason why we have this inverse is because we are taking derivative at two different points. Here we're taking derivative at x naught. Here we're taking at y naught. So that's why we need to compensate this by some f inverse. But the general idea is that they're symmetric, so then the slope are reciprocal of each other. So maybe we can just try to use the fact that e to the x has the derivative equal to itself. Then we can take this as f of x. Then this means f prime of x is equal to e to the x. And then we can use, and also we know that f inverse of x is ln of x. So we can actually use this to compute or to check that the derivative of ln of x is indeed 1 over x. What does it mean? It means that we're taking this ln of x as f inverse of x, right? Where f is the exponential function. We know what's the exponential function and then its derivative. and then we know ln of x is its inverse, which means we can use the rule to calculate the derivative of its inverse, which is f inverse prime of x, right? So then we can cancel, we can find this value. So then by this rule, this will be equal to 1 over f prime of f inverse of x, right? But then what is f prime of something? F prime is e to this guy. So this is e to the f inverse of x, right? But what is f inverse of x? F inverse of x is ln of x. So this is 1 over e to the ln of x. And then because they are inverse of each other, so e to the ln of x must be x. So then this is 1 over x. Does that make sense? So this actually gives another proof of that. So this is what you can do with the inverse functions. And if you play it with all the arc, with all the inverse trigonometric functions, then what you can get is the following formulas. The first one is the derivative of arc sine. I mean, I will talk about arc sine maybe later, or maybe in this video. So then this is 1 over square root of 1 minus x squared. And then arc cos is simply negative 1 over square root of 1 minus x squared. And then arc tangent of x has its derivative equal to 1 over 1 plus x squared. And then arc of cotangent x has its derivative equal to minus 1 over 1 plus x squared. And if we talk about arc of secant of x, then the derivative is equal to 1 over the absolute value of x times the square root of x squared minus 1. And then the derivative of arc cosecant is simply minus 1 over absolute value of x times square root of x squared minus 1. And then one might be interested why. Here it's much simpler that when we talk about the cotangent and then cosecant, then simply just take the minus of the previous one, right? Which means all we need to do is just to memorize these three formulas. But why is that? And the reason is by definition, the arc sine, arc cos, arc tan, arc cot, arc secant, arc cosecant are just inverse of the previous function on some good interval. Okay? Because sine itself is not, I mean, I will talk about it later. But the point is that we know that, for example, sine of pi over 2 minus x is equal to cos of x. So if you just play with this, and then you will see that the arc sine of x must be equal to pi over 2 minus arc cos of x, okay? Because they have this relationship. I mean here, this x is the angle, and arc sine, arc cos are both the angle. So you can see they have the symmetry, right? Their sum should be pi over 2. So then you get this. So then what I mean is that you actually have this formula. So I mean you can just do up to this step, and then you win. Because if you take the derivative with respect to x, then pi over 2 goes to 0 because it is a constant, right? The derivative of a constant is 0. So this means the derivative of arc sine is minus, or let me just put it this way, the derivative of arc cos is equal to minus the derivative of arc sine. And you win. So that's why, and then you can do the same thing with arc tan, arc cot, and arc secant, arc cosecant, because by definition, you can do that, okay? And so one can prove easily that this is true, but one has to be careful about the definition of x and also what the quadrants are to make sure that you have the correct sign. So for example, here you don't have any, it's just plus 1. Here it's just plus 1. But here it's plus or minus 1 depending on the absolute value of x, right? I mean here it's always positive. I mean, but you cannot just simply write x. It's absolute value of x, which means you have to be careful of if it's plus or minus, right? And up to this point, I have talked about basically almost all the proofs. So maybe I can just continue from now on. Let me just continue. What's arc sine and what's arc cos? So let's look at the graph of sine of x. As I said here, it should have slope 1, right? Okay, so this is the graph of sine, and then you can see that this function is periodic of period 2 pi. And also it is symmetric along this guy, which is pi over 2, right? Because this is 0, this is pi over 2, this is pi, this is 3 pi over 2, and then this point is 2 pi. It is actually symmetric along this point. It's symmetric along x equals pi over 2, which means if you reflect the graph of the left to the right, then it coincides with the graph on the right, okay? And then also, it's actually symmetric along x equals 3 pi over 2 and then minus pi over 2. Or it's actually symmetric along all the pi over 2 plus any k pi, where k is an integer. Okay, but it doesn't matter. So you can see that the graph, so if we consider this function sine as a function from r to r, then this is clearly not surjective. Why? Because all the values must be within -1 and +1, right? Because the range of sine is equal to the interval, the closed interval from -1 to 1, because we can attain the -1 and 1 at, for example, minus pi over 2 and pi over 2. Which means if we want to make this sine surjective, then we have to change this r into a smaller set, which is just the closed interval -1 to 1. So then if we do that, then it will be surjective by this choice, right? So then this will be surjective. But it's not injective. Why? Because, for example, for any point that are symmetrical along pi over 2, they have the same value. So what you want to do is that you just want to find a sub-interval such that it is 1 to 1. And then a perfect choice is just from minus pi over 2 to pi over 2. Just look at this one. Then you can see that it will attain every value from -1 to 1 at exactly once, right? Because on this interval, if you look at the graph, if you look at any value from -1 to 1, let's look at 1/2, then it intersects with the purple curve at exactly 1 point, right? I mean, at this point, it is the value is exactly the 1/2. So you can do it with every horizontal line, and you will see that it will pass the purple part exactly once. And you have to be very, very careful. So here it is the closed interval from minus pi over 2 to pi over 2. If you choose this, then it becomes injective and surjective, which will bring together into bijective or invertible. I mean, they're equivalent. So then you can find an inverse of that. Because it's bijective, then you can find an inverse. And it's not hard to just find this inverse. You just do some little work, then you just flip the graph along y equals x, then what you get is arcsine. It's something like this. Okay, so then this is the graph of arcsine. I mean, you have to make sure that here the slope is about 1. And then this is arcsine. And here it's then you want to change this from -1 to 1 to minus pi over 2 to pi over 2. So this is -1, this is 1, this is minus pi over 2, this is pi over 2. And it's clearly increasing. And then if you put the graph together, you can see that they are symmetrical along y equals x. Okay? So this is the part of sine. And then this is arcsine. They are symmetrical along y equals x. And also, if you look at any point x in this interval -1 to 1, then you take arcsine, because it's in the domain, right? It's in the domain of arcsine. And then you take the sine. Then it's clearly equal to x, because by definition of inverse function, that's how you choose arcsine. And similarly, if let's say x is in negative pi over 2 to pi over 2, then clearly arcsine of sine of x would be equal to x by definition, right? Because they're inverse to each other. But we actually have a problem of arcsine of sine of other values, and that would be a problem. But we can solve it. So for example, but I mean, note that this function is defined not only on the interval minus pi over 2 and pi over 2. It's defined everywhere, because for each x in R, sine of x is in the interval -1, 1, which is exactly the domain of arc sine, which means you can say what this value is. So this function can be extended to a function on R, which means you can define this on every real number. But then you might be interested what this will be like. So the first thing that we should know is that arc sine of x plus some 2 pi must be equal to arc sine of x, which will give you x if x is in the interval minus pi over 2 to pi over 2, right? Why is that true? Because sine is periodic of period 2 pi. So you can also change it into any 2k pi, right? Then for any k in z, if x is in the interval, then this becomes x. But what does it mean? You can do it for all the. So let's look at the graph of arc sine of x. So we can look at this. We can call it f of x. Then you can see that the graph, at least for the point x from minus pi over 2 to pi over 2, right? Then the graph has to be coincide with y equals x. So which means if you look at minus pi over 2 to pi over 2, and then you look at minus pi over 2 and pi over 2, then what you have is this graph, right? This is arc sine of sine x. It will be equal to x in this area. And then if you look at pi, and then if you go to, for example, 3 pi over 2, and then you go to 2 pi, because this is also, by this it means that it is symmetric, right? It is symmetric, also it is also periodic of period 2 pi. So by this, for any value, for example, for the value at 3 pi over 2, this is minus pi over 2 plus 2 pi, right? This is minus 2 pi plus, this is minus pi over 2 plus 2 pi. So when you take ak to be 1, and then you take x to be minus pi over 2, then it is at the same value. So which means you have this, on the graph, you will have this point. So similarly, you can just have this part. Also, it has slope 1, like have like a degree 45. So let me sketch it. I'll try to make it better. Okay. So then this is also the graph, and you can do it infinitely many times. You also have some graph here, some graph here, but it's not a complete graph. You also need to know what's the value here, right? And then you can complete the graph, but not to forget that sine of x is also symmetric along x equals pi over 2, right? Remember, it is symmetric along pi over 2, which means if you take arc sine of the same thing, if you take arc sine of sine, then it is also symmetric along x equals pi over 2, which means whenever you know the graph on the left of pi over 2, you can simply reflect the graph by the symmetry. So by symmetry, you can simply say that you can reflect the graph and then continue. And as long as you have this, you're done, because this has length pi. This has length pi, and this has length also pi. So then this is a complete period, and this guy is also periodic of period 2 pi. So which means you can just continue. So which means, geometrically speaking, the graph of arc sine of x will just be like something like this. Okay, I mean it's not a good graph, but it should be the slope should be +1 -1 +1 -1, and then here you start with minus pi over 2, and then here the length is pi, and then pi, and then pi, and then pi, and then pi. Okay, so then for each value you can just do some manipulations. You can bring it into somewhere here. I mean, if the value x is very big, then you can subtract by some 2 pi, and then some 2 pi, and then some 2 pi, until it is here, until it is somewhere here, right? Because this is in an entire period. And if the value x is very small, then you can make it bigger, and until it lies here. Then you switch into then you have two cases. So here, let's say if you have some x that is on this interval minus pi over 2 to 3 pi over 2, then what is its value? You can just look at the graph, and it's very clear that if x is kind of small, like if it's between minus pi over 2 to pi over 2, then this value is simply x by the definition of the inverse function. But if x is big, let's say if it's from pi over 2 to 3 pi over 2, then you can see that the value here should be the value exactly over here, right? And they are symmetric along x equals pi over 2, which means this arc sine of x must be equal to arc sine of pi minus x, right? Because if this is x, then this must be pi minus x. Why? Because the sum, because pi over 2 is the midpoint of these 2 points. So maybe we would call it x prime. Okay? So pi over 2 should be the midpoint, which is of x and x prime. So it should be x plus x prime divided by 2. So then this means that we can cancel out 2, so x prime must be pi minus x. Okay? So this must be pi minus x. So if we want to look at the arc sine of pi minus of x, it's just arc sine of sine pi minus x. And then if x is in this interval, then clearly it says that pi minus x is in the correct interval. Then this will mean that this is pi minus x. Okay? Which means we can use this to solve arc sine of x for any x, and then we can find the correct formula. And similarly, we can do it with arc cos. And if arc cos, it's slightly different. The graph is like this, right? Here it's 0, and then go to pi over 2, go to pi, go to 3 pi over 2, and then go to 2 pi to form a entire period. Go to 2 pi. Okay, so this will be an entire period, but it's not 1-to-1, so we choose just one of them. So maybe we just choose this one, okay? So also from -1 to 1. Then if we look at the graph, if we look at cos, that's from 0 to pi. We look at this restriction, or we look at part of this function, this part. Then this cos will be also bijective and invertible. Or invertible. Then we will call that then we will define arc cos to be the inverse of this function. So then you can also have the graph, and then you will also see that now this is symmetric along pi, not just pi over 2. It's symmetric along x equals pi. And then, so maybe if you wish, we want to sketch the graph of arc cos of x. Then at least for all the point x in the interval 0 pi, then it must be equal to x, right? It must be equal to x. So from 0 to pi, it must be like this. And then cos is symmetric along x equals pi. So then the entire thing must be also symmetric along x equals pi, which means you can just reflect the graph. So then you get the graph of from pi to 2 pi. So it should go down to 2 pi. And then this graph this function arc cos of cos is periodic of period 2 pi, which means we can just find the entire function, okay? Arc cos of x. So you can just play with the symmetry and the periodicity, and then you can get the graph, which means, so now you can just play with it, and then for each value x, you can plus or minus some 2k pi until you get some value, let's say, so within 0 and 2 pi. So maybe we can just assume, without loss of generality, that, so now let's just consider the case when x is in 0 and 2 pi. Again, if x is in the correct interval 0 pi, then arc cos of x should be just x. But if x is big, let's say if x is from pi to 2 pi, then we need to find the point that where it is good enough. But here it's symmetric along pi. So if this is x and this is x prime, then the midpoint is pi. So which means x plus x prime over 2 should be pi. So this means x prime is 2 pi minus x. Okay? So this means this point should be 2 pi minus x, which means now this arc cos of x should be equal to arc cos of cos of 2 pi minus x, because cos is periodic, cos is symmetric along x equals pi. So then this will be, now 2 pi minus x is in the correct interval. This is in the interval 0 pi, because you can just see it from the graph, right? Because 2 pi minus x, if x is here, then 2 pi minus x is just here, which is the correct interval. So then this will be just 2 pi minus x, okay? So then you can solve for arccos of cos for every x. And similarly, you can do it for arctangent of tangent of x. And if for tangent of x, we usually just choose this one for sure, okay? So this is tangent of x. And then this is minus pi over 2 and pi over 2. So we choose this, and then we take its inverse. We can define arctangent. And then the interesting about tangent is that it's different from sine and cosine in the sense that it's not symmetric along any x equals something. It's only periodic, but it's not symmetric along any line, right? Because it's just continue going down. Not like sine, like it will go up and then go down and go up and go down, right? It's not symmetric. It's only periodic. So that's why if you sketch the graph, it will be different. So maybe you can just take it as an exercise to compute what is arctan of 10. It'll be similar, but you will not see it will go down. It will only go up, and then go up, and then go up, and then go up. It will be like this.